Let's talk about the classic kinematic learning objective. That is, I can use the basic kinematic equations and some of the characteristics of motion to predict other characteristics of motion. What exactly do I mean by these characteristics of motion? So we've already learned them, velocity, acceleration, position, or displacement. Those are the characteristics. So the idea is that we are going to use equations and some of the characteristics, so maybe position and velocity. And then we're going to find acceleration. Or, maybe we have time and position and acceleration. We're going to find a final velocity. The idea is that we're using some characteristics that we have the value for. Maybe we just know what the velocity is. And we're trying to find some of the other values. These below are going to be the 6 kinematic equations that we are going to use in this class. The very first one, we have x is equal to x naught plus v naught times t plus 1/2 acceleration times squared. Now this x naught and v naught business also means it's essentially initial position and initial velocity. So what this is saying is that the position at a later point in time is equal to a starting position, and a lot of times this is going to be 0, plus an initial velocity, so how fast you were going at time equals 0, times the time that has elapsed, plus 1/2 of the acceleration times time squared. So as long as you have acceleration, then you'd multiply it by the time it takes squared, divide it by 2, and then add it to the velocity, initial velocity that is, times the time, and you'll get the position at a later point. That is called the position equation. We also have what we're going to refer to as the velocity equation, and that is velocity at a later point in time, so some later velocity after a given amount of time, is going to equal how fast the object was going, plus the acceleration times the time. Now let's just quickly understand, why is it acceleration times time? Well, acceleration is defined as the change in velocity over time. So if you multiply that by time, you're going to get a change in velocity. So it's essentially how fast did it start, and then what was the change in velocity. This last equation on the left-hand side is unusual but very useful if you don't have time. Notice these other two equations had time in it. But let's say you didn't know what the time was. You didn't know how long something elapsed. You didn't know how long something was traveling in terms of time. But maybe you knew how fast it ended. What was its final velocity? You knew what its initial velocity was. You knew how fast it was accelerating. And you knew where it started and what position it ended at. That would be when you would want to use the velocity squared equation right here. So if you don't have time, typically this is the equation you're going to use. Now on the right, we have 3 other equations. One is just defining what average velocity is. And so that's just the final position minus the initial position divided by time. We've kind of talked about this already in a previous video. And then we have another definition for average velocity. And that is equal to the initial velocity plus the final velocity divided by 2. Now, I want to point something out here. This average velocity, and in fact, actually all of these equations that we've been talking about so far, only work if we assume a constant acceleration. If we do not have a constant acceleration, then none of these equations are valid and you should not use them. But under the case that they do have constant acceleration, then these can be applied. Now, what does constant acceleration look like? Well, first off, let's take a look at a velocity time graph. We've already gone over these velocity time graphs, position time graphs, acceleration time graphs. But let's take a look at this velocity time graph. Here we have a line going up. It's not a horizontal and not a vertical line, but a sloped line going up in a positive direction, with a positive slope, I should say. And the characteristics of a line is that the slope is always the same. The slope does not change. The rise over run remains the same for the entire time. Now, if we remember, the slope of a velocity time graph is the acceleration. So this would mean that under this circumstance, we would have a constant acceleration. Acceleration equals the change in velocity over the change in time, or the rise over run. So for this case, under this situation, this would be a constant acceleration. If it's a constant acceleration, these equations I showed you before are valid. And one of the equations I want to highlight here is this equation, the velocity equation. The velocity at a later point in time equals the initial velocity plus acceleration times time. What's interesting about this is this should look very, very, very similar to an equation that you've already worked with in your algebra class. Y equals mx plus b. Here I wrote it as y equals b plus mx, but you should know that that is the same. The reason I did that is because these variables right here, velocity initial, acceleration, and time, have an analogous representation in this y equals mx plus b. The initial velocity is going to be your b, and if you remember from your algebra class, b is your y-intercept. It's where you cross the y-axis. And sure enough, that's going to be where your initial velocity is, because at time equals 0, you start with a velocity, and that's your initial velocity. So that's your y-intercept. So that's your b. Acceleration we've already defined as the slope of the line, so therefore it's m. And then for the x, it's a little confusing because in math class, typically they use the x on the x-axis. Makes sense, they even named it that. But here we are using time in our x-axis. So t is our x. Let's go over the steps to solve a kinematics problem. The first step is you are going to read the problem and draw the situation. Now, not always do you need to draw the situation, but I would highly recommend it. In physics in general, I would always recommend that you draw your problem. I cannot solve a physics problem without drawing it out. It is incredibly handy to really wrap your mind around such abstract things, to get a good picture of it. And in fact, when we get to forces, it's going to be a very particular skill that I'm going to teach you on how to do, calling drawing free body diagrams. The next thing you need to do is to identify the variables. So what variables are you given, and what variables is the problem trying to have you find? Then you're going to determine which equation would be the most helpful. Then, step 4, you're going to rearrange the equation to solve for the unknown. And then lastly, you're going to plug in your values. And of course, plug it in your calculator, solve it, write your final answer with the appropriate units. Those are all just taken for granted. Let's look at a sample problem. So in this problem, we have a car traveling at 30 meters per second. So 30 meters per second, that's going to be a velocity. But we should also be aware, this is what the car starts at. So this is our initial velocity. So a car traveling at 30 meters per second puts on its brakes. The car decelerates at -5 meters per second squared. So we should recognize right there that that is an acceleration. For 4 seconds, that is a time. How far did the car go during that time? So I read the problem. Let's go ahead and draw this situation. So we got a car. Fabulous looking. And it is going with an initial velocity of 30 meters per second. And it's going to be doing that for 4 seconds, but it has a deceleration that's going in the opposite direction. So the acceleration is that way. And what we're doing is we're going to figure out how far did it travel? In order to solve a kinematics problem, we need to recognize the 6 kinematic variables for the problem. Each of these problems have a set of 6 kinematic variables. It's the initial position, the final position, the final velocity, the initial velocity, the acceleration, and the time. Now, not every problem is going to use all of them. You just need to choose an equation that has all but one available to you. So we read the problem, we drew it. Now we need to identify our variables, which we've already been doing while reading the problem, but we should write them down. So first off, the final position, we don't know it. It's a question mark. In fact, that's what the question is asking us for. Our initial position was never mentioned. It never specifically mentioned a starting position. When that happens, you should always assume that it starts at 0. Now, the final velocity was not given, and it wasn't asked for. So we don't know that one either. The initial velocity was given to us. That was 30 meters per second. And it was a positive 30 meters per second. We're going to define, one thing we haven't done yet, but we should do, is we need to declare which direction is positive and negative. To the right is going to be positive for us in our drawing. The left will be negative. That's why the acceleration was to the left and the initial velocity was to the right. The acceleration is -5 meters per second squared, and the time elapsed is 4 seconds. We have now done the second step of identifying all the variables. Now what we need to do is we need to identify which equation is going to be helpful to us. Since this is asking for position, and it gives us, since this is asking for position, it's what we're looking for, we have the initial position, because we're going to set it to be equal to 0. We have the initial velocity, we have the time elapsed, and we have the acceleration. We have all the variables of the position equation, except for, of course, the later position. So we're going to use that equation. X is equal to x naught plus v naught t plus 1/2 acceleration times squared. The next step would have been to rearrange that equation. But lucky for us, it's already solving for the variable that we are looking for. So we don't need to rearrange anything. Finally, we're going to plug some stuff in. So the initial position is 0. So that simplifies some things. So we get x is equal to our initial velocity, which is 30 meters per second, times our time, which is 4 seconds, plus 1/2 the acceleration, which the acceleration is -5 meters per second squared. Don't forget that negative. And then our time squared, which is 4 seconds squared. That's going to get us 4 times 30 is 120. Now, meters per second times seconds is just going to give you meters, plus 1/2 acceleration, which is -5, times 4 squared, so 16. So -5 meters per second squared times 16 seconds squared. Now also notice the second squared and the meters per second squared is going to cancel all the second squareds. Both of these terms are going to end in meters. And that's actually important because we can only add 2 units that are the same. You can only add 2 numbers if they have the same units. It wouldn't make sense to add a meter and a kilogram. What does a meter plus a kilogram even mean? One's a measurement of mass, one's a measurement of length. So we have to add 2 units that are the same. What's interesting is this first part was the initial velocity times the time. So this distance right here, this 120 meters, kind of represents how far would it go if it didn't accelerate or decelerate at all. Like if it didn't have any acceleration, if the acceleration was 0, that's how far it would go. And in fact, if acceleration was 0, that whole right term would just go away. So that first term represents how far it would go without acceleration. And then we have the acceleration, which this whole term on the right side is going to be negative. And because it's negative, it's going to be subtracting from the first term. So that means this last term right here is essentially how far did it not go because it was accelerating. Let's finish this problem out. So we got x equals 120 meters plus 1/2 of 16 is 8. 8 times 5 is 40. So plus a negative 40 meters. So 120 meters plus a negative 40 meters is equal to 80 meters. So our final position is at 80 meters to the right of where it started. And let's go over another example. So in this problem, we're again going to use the position equation. Let's read it together. So a spaceship ignites thrusters in space and starts accelerating at a very small acceleration of 0.1 meters per second squared. So what did it do right there? It gave you the acceleration. If the spaceship starts at rest, that is a key phrase right there. If you read a physics problem and it says started at rest or starts at rest or comes to rest, what it's saying is velocity is 0. So that's our initial velocity and it's 0. How long? How long? That's a key word for time. So time is a question mark. We don't know it. Would it take the spaceship to reach a distance of 20,000 meters? So that right there is our final position. So we've read the problem. Now we're going to do the step of identifying the variables. So final position is 20,000 meters. Initial position, it wasn't explicitly stated, so it's 0 meters. Final velocity was not said. Initial velocity was 0 meters per second. Acceleration, 0.1 meters per second squared. And time is a question mark and is in fact what we are looking for. So let's go ahead and use the equation, the position equation. X is equal to x naught plus v naught t plus 1/2 acceleration times squared. Let's go through this equation and try to identify if this is the right one for us. So do we have the final position? Yes. Do we have the initial position? Correct. Initial velocity? Yes. Time? No, we don't. Plus 1/2 acceleration. Do we have acceleration? Yes. Do we have time again? No. Now it might look like we have two unknowns, but we actually just have one unknown that shows up in two different terms. So this is solvable. And in fact, it is much easier than it looks, because let's do the step where we plug in some zeros. Before you rearrange, you're allowed to plug in one thing, and that is zeros. Any variable that has a value of 0, I highly recommend to plug in to your equation before you rearrange, because it's going to simplify things down. So the initial position is 0. The initial velocity is 0. So 0 times time is still 0. And then we have the 1/2 acceleration time squared. So that means this equation just becomes x is equal to 1/2 acceleration time squared. That's it. So you can see how plugging in zeros anytime you have a value of 0 can really help simplify a problem down. All right, now we need to rearrange the equation to solve for what we're looking for. And we're looking for time. So let's go ahead and rearrange this equation to solve for time. We're going to multiply both sides by 2. So we get 2x equals acceleration times squared. Then we're going to divide both sides by acceleration. That's going to cancel acceleration on the right side. It moves it to the left side. And then lastly, we're going to take the square root of both sides. So time would equal the square root of 2x over acceleration. Now, technically, it's plus or minus. Your math teachers will be very particular about that. It's plus or minus the square root of 2x over a. But here in physics, we're going to constrain it to values that make sense for the problem. We're not considering negative time. You can consider negative time, and a lot of physicists actually do consider negative time. But we're not going to consider negative time. So for us, it's only going to be the positive version. So time is equal to the square root of 2x over a, which we can now plug in the values for. So that's the square root of 2 times x, which is 20,000 meters, all over the acceleration, which is 0.1 meters per second squared. And you can plug that in a calculator and get your answer. Now, one thing I want to point out is, why would this work unit-wise? Let's take a look at just the units. We have the square root of meters divided by meters per second squared. That's the same thing as the square root of meters times seconds squared over meters. We're going to use that trick that if you're dividing by a fraction, it's the same thing as multiplying by the reciprocal. That cancels the meters, and then we get the square root of seconds squared, which is just seconds. So that's why, unit-wise, this works out. Whenever you do a physics problem, you can also check whether your answer makes sense by checking whether the units canceled in just the right way. Now let's take a look at another physics problem. This time we're going to use a different physics equation for this one. So we have a soccer ball is kicked from rest. Oh, there's that keyword again. From rest means initial velocity equals 0 meters per second to a velocity of 25 meters per second. If the acceleration was 500 meters per second squared, how long did it take the ball to accelerate to that velocity? So how long, we're talking about time, and then this value given right here was the acceleration. So we've read the problem. Let's identify our variables. We were not given an initial position or a final position. We were given a final velocity. That was 25 meters per second squared. Nope, not squared. 25 meters per second. And we were given an initial velocity of 0 meters per second. And we were given an acceleration of 500 meters per second. And we weren't given a time. The time was unknown. Now, it wouldn't make sense to use the x is equal to blah, 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 blah equation because we don't have x and we don't have the initial x. So that equation doesn't make sense to use. Let's keep our eyes on the prize. What are we even trying to find? We're trying to find the time. So our equation needs to have time in it. So the velocity squared equation doesn't make sense. So that leaves us with one equation left. Velocity at a later point in time is equal to the initial velocity plus acceleration times time. Let's go through this equation and check the variables to make sure that this is indeed the right equation to use. So starting with the final velocity, do we have a velocity at a later point in time? Yep, we do. Do we have an initial velocity? Yes. Do we have an acceleration? Yes. Do we have a time? Nope, we do not have a time. So let's go ahead and rearrange this equation. Before we do that though, remember my one exception to the rule of always rearrange then plug in values is that we could plug in zeros right now. So let's go ahead and do that. Our initial velocity was the value that was 0. So we got a final velocity equals acceleration times time. Then we're going to rearrange that and solve for time. Time is equal to velocity over acceleration. This kind of algebra manipulation skill is incredibly handy to have when doing a physics problem. So now let's go ahead and plug in some values. Velocity of 25 meters per second and divided by 500 meters per second squared. That's going to get us in the end just seconds left. And looking at this problem, if we were just dividing 25 by 5, we would get 5, but it's divided by 500. So instead of 5, we would have 0.05 seconds. And finally, let's use this last equation, the velocity squared equation, just to see an example of when this would be useful. So an object experienced an acceleration of 20 meters per second squared. So again, we're given the acceleration. If it started at rest, velocity initial equals 0. Love to see it. How fast is it going? So that's going to be our later velocity is the question mark. That's what we're solving for. After it travels 5,000 meters. So that is our delta x, or our final minus our initial. If you make the initial 0, it's just our final position. So we can actually go ahead and do that. Let's make the final position 5,000 meters. Initial position 0. Final velocity is what we're looking for. Initial velocity is 0 meters per second. And acceleration was 20 meters per second squared. And we were not given time, nor are we trying to find time. That is your big clue that we should use this velocity squared equation. We have initial and final velocities and no time. Velocity squared equals initial velocity squared plus 2 times acceleration times the change in position. Let's see if we have any zeros. We do. We have our initial velocity is 0, so we can get rid of that right away. Final velocity squared is equal to 2 times acceleration times the change in position. And what are we solving for? Looks like we're solving for a final velocity, so we're almost rearranged for the equation. The only thing is we need to take the square root of both sides. So we get the square root of 2 times the acceleration times the change in position. And technically it is plus or minus. But for this problem, we are only going to consider the plus case. Because it had a positive acceleration, it started at velocity equals 0. So when time progresses, this object is only going to be going in the positive direction. If we let time go in the reverse, it would be in the negative direction. Finally, plug in our values. So that's the square root of 2 times the acceleration, which is 20 meters per second squared. All times our change of position, which is 5,000 meters. Plug that in your calculator, and you'll get your answer. Let's just go over the units really quickly. What we have is a square root of meters per second squared times meters. That's going to get you the square root of meters squared over second squared, which is going to get you meters per second. So do we have the correct units? Yes, because we're trying to solve for velocity and we got meters per second. There is one special case we need to consider when talking about kinematics, and that is when we have gravitational acceleration. So this is a special case where the acceleration is caused by gravity. So if you drop an object, in other words. And we're not going to be considering the case of dropping down a ramp. Its acceleration won't be the same then. We're talking about if an object is dropped and it's not touching anything. It's in what we call free fall. It's not in contact with anything. There's no other forces acting on it other than gravity. Now, we have some assumptions that we need to talk about. So the assumptions we need to talk about are that we are assuming that the object is being dropped near the Earth's surface. If you go to the moon and you drop an object, it will fall slower than if you drop an object on Earth. So the acceleration is different on the moon than it is on Earth. So we're going to assume that the object is being dropped on Earth's surface unless otherwise stated. We are also going to assume no air resistance. Under that case, under that circumstance, acceleration is going to be equal to 9.8 meters per second squared. And this is so special in physics, we give it its own letter to represent that. A little g. Little g here represents 9.8 meters per second squared. So sometimes when we have an equation like, let's say this equation, x is equal to 1/2 acceleration times squared, we might replace the acceleration in that equation with 1/2 g times squared. Just be aware when you do that, you need to account for direction. So if you assigned down as negative, then it's going to be x is equal to 1/2 negative g t squared. So you still need to keep account the direction, and it all depends on whether you set call down as negative or down as positive. But the value, the magnitude of it, is going to be 9.8 meters per second squared. Let's take a look at another problem, this time using gravitational acceleration. So you throw a ball straight up with an initial velocity. So here we are given the initial velocity of 30 meters per second. How long does it stay in the air? So this is time that we're looking for, until it returns to where you threw it. Now, looking at this problem, it's going to seem like we were not given enough information. We have been only given explicitly one number, and that is 30 meters per second as the initial velocity. But there are some other values that we are given that are not explicitly stated. The first value is that we are given acceleration. It is negative 9.8 meters per second squared. And just make sure you recognize that this is negative 9.8 meters per second squared because we're going to be calling down as negative, because you threw it up with a positive velocity, so up must be positive. Now let's go ahead and put in our initial velocity as 30 meters per second. Now, to do this problem, we need to understand something about throwing an object up in the air. If you throw an object up in the air, it's going to go up and then come back down. And it turns out that the time it takes to go up is the same amount of time that it takes to go down. So there's a couple things we could do here. We could just consider the case where it goes up to the top of its arc. And we could just solve that physics problem. That is usually what I like to do. So let's do that. We're going to say that it's just going to go up, and we'll consider the case where it comes back down later. What is the final velocity when it's at the top? So I want to signify here, this is going to be at top. And so will the time. The time will also be at the top. The velocity at the top is actually going to be 0 meters per second. And if you think about throwing an object in the air, you throw it up, and right when it hits the top, it seems to momentarily stop, be frozen in time before it comes back down. It's instantaneous. But for a brief, instantaneous moment in time, its velocity is 0. So we have 0 meters per second. With these 4 variables, we actually have enough to use a physics equation. The physics equation we're going to be using is velocity is equal to initial velocity plus acceleration times time. We are looking for acceleration. We're looking for time. We have acceleration, we have initial velocity, and we have a final velocity. So let's rearrange this equation and solve. Now we notice that the final velocity is 0. So 0 is equal to 30 meters per second plus the acceleration, which is negative 9.8 meters per second squared times time. And I just noticed that I did not follow my rule of rearrange first, then plug in. We could just do that really quickly. We would have negative initial velocity is equal to acceleration times time. So therefore, time would equal negative initial velocity divided by acceleration. So for our case, time is going to equal negative 30 meters per second divided by the acceleration, which is negative 9.8 meters per second squared. And that's going to get us our final time. Now, we should notice here, the negatives cancel out. This is super important. If we did not put the acceleration as negative 9.8 and just use 9.8 instead, we would get a negative time, which for this problem doesn't make sense. So plugging in our calculator, what we're going to get is 3.06 seconds as our final answer, but it's not our final answer actually. This is just the time it takes to get to the top. So what we need to do is multiply that by 2. So the total time is going to equal 6.12 seconds. That is a strategy you can also often use in a physics problem, is break the problem into multiple problems. Lastly, I'll leave you with a couple of practice problems. So you'll have to apply the steps that you should have hopefully written down in your notes. First one is a bullet leaves the rifle of a muzzle with a velocity of 521 meters per second. While accelerating through the barrel of the rifle, the bullet moves a distance of 0.840 meters. You're going to determine the acceleration of the bullet. And I give you the answer for it, so you can check your work, but you're of course going to do the work for it. And lastly, a baseball is popped straight up into the air and has a hang time, so that means that's in the air for 6.25 seconds. Determine the height to which the ball rises before it reaches its peak. So, in other words, how far did it go up?